Okay. So there was a problem with the recordings from last week. Apparently my microphone was off, so there is no audio on the recordings, which is, I guess, waste of recording, right? Well, what I'm gonna do, we have a couple of students who are complete remote students, right? And this is nothing official, it's just between me and them. I'm going to have a meeting with them and record that class and upload that class online, right? I will open it to everyone in class. Whoever wants to join and ask questions, they are welcome to. But it is not an official class. It's just a meeting between me and them. Okay, does this make sense? Yes. Okay. Yes. Pardon me?
Is there a time for those meetings, like set?
No. It will probably be either during the weekend or on a Friday, this Friday. But I have to reach out to them. I don't remember how many students they were. There were a couple. I'm not sure. So I'm going to ask them to go over the lecture notes and ask their questions. So if they had a specific questions, I will go and answer the questions. So if you have a question, you can come on board and come to the lecture and ask your questions as well. I will try to explain, right? But it is going to be a little more explanation than just a regular question in class, right? I will just go over the topic. Any questions? Okay. If you are a graduate student, meaning that if you are registered for 744 and you have to choose your topic for the project, make sure you do so as soon as possible, because your project proposal deadline is coming up, and that is of course graded, right? But if you are not, you don't have to worry about anything. We will go over the project on Thursday. So I will upload a couple of documents, like templates, and for presentations for the project final report. And we explain the grading criteria in class for like 15 minutes in the Thursday class. So make sure to come prepared if you have any specific questions about the project, right? And I would recommend start working on the project as soon as possible. Don't delay work on the project. It can be a very time-consuming part of the class. So, if there is no question, let's continue the discussion. We were going to start working on governing equations. And this is the governing equations of the fluid flow in general. There are three main equations that we are going to go over. First one is conservation of mass. Second one is momentum equation, or linear momentum equation actually. And the third one is the energy equation. For incompressible aerodynamic applications, the energy equation doesn't really play a role that much, right? But the energy equation talks about the energy transfer and temperature change. When you are in the incompressible region, we don't really care about temperature change that much, right? It's not that effective, unless you are specifically talking about the temperature change, like heating of an airfoil, right? Then you have to include the energy equation. So we are mainly going to focus on these two and their applications. Okay. Before doing so, we need to have a couple of things introduced. The first thing is a control volume. Who can tell me what a control volume is?
Is it a volume specified by boundaries?
A volume specified by its boundaries. And what is so special about this volume?
There's no delta. There's no change in it.
There is no change in the volume. So essentially, you have an arbitrary volume that you choose in a space. You can have energy transfer or mass transfer from its boundaries. Mass can come in and go out of the boundaries. You may have energy generation inside. Think of chemical reactions, right? That are going to generate some energy inside. And the rate of mass inside the volume can change. So when it comes to mass, the relationship between incoming, outgoing, and outgoing mass is going to give us the conservation of mass on a control volume. The same is true for linear momentum, mv, right? So the changes of linear momentum and the relationship to forces is going to give us the conservation of the momentum equation. And energy, essentially the rate of change of energy inside a control volume is going to give us the energy equation. We are not going to go over the derivations of these equations though, but the derivations are all in the book. We'll talk a little bit about them. The other thing we need to talk about is the divergence of velocity. What is divergence of velocity? Velocity itself in Cartesian coordinate system is a vector with this components. And if you were to calculate the divergence of velocity, we are going to get this value, right? Partial u partial x, partial v partial y, partial w partial z. But what does this signify? The divergence of velocity. What does this show us?
Scalar component.
What?
Scalar.
A scale?
Scalar.
No. It is a scalar component. But this value, let's say I say the divergence of velocity is 5. What does it mean? What does that 5 mean? First of all, what is the dimensions of divergence of velocity? What is the dimensions of velocity? Meters per second. What is the dimensions of divergence of velocity? It's meters per second. What is this? Meters. So per second. That's the dimension of divergence of velocity. So what does it mean? I said that the divergence of velocity is 5 per second. What does it mean? Any ideas? Rate of change of what? Rate of change of the volume of your system. Essentially means that if your divergence of velocity is 5, then your volume is, the volume of that fluid element is becoming 5 times bigger each second, right? Does it make sense? Think about it this way. The velocity itself in each direction is the movement in each direction. If you are moving in all directions, you are expanding, right? In all directions. Divergence of velocity. So this rate of change of volume is going to come back and help us in developing these equations. Okay. So based on this idea, let's get to the mass conservation equation. What does mass conservation equation tell us? Tells us mass is conserved, right? What does it mean? It means it is not generated? Yes.
It means that the mass coming into the system is going to be equal to the mass coming out of the traditional volume.
Exactly. So mass coming into the system is going to be equal to the mass going out of the system, right? And how can we characterize this? First of all, the derivation proof of this has a bonus point. So essentially, if you submit the derivation of mass conservation, you will get a bonus point. And it's going to be due Thursday. So Thursday, what is the date? 27th, right? Thursday is 27th. Before the class. You'll get a bonus. We are clear on what the bonus points are, right? And the derivation is in the book. You can just go on the book and you copy it and submit it. What does the equation itself tell us? It tells us we usually talk about density, mass per volume, so volumetric mass, right? Or a specific mass, which is density. It tells us that the changes of density, over time, plus the changes of density multiplied by velocity in the x direction, plus the changes of density multiplied by velocity in the y direction, plus the changes of density multiplied by the velocity in the z direction has to be equal to 0. Okay? We can actually rewrite this as partial rho partial t plus the gradient of rho v. Combine all of these together. How can we this is the general equation. This is the general, it's called the general differential form of mass conservation. How can we simplify this for an incompressible flow? First of all, what is an incompressible flow? Density remains constant, exactly. So based on this, how can we simplify this conservation of mass? Partial rho partial t is going to be 0, right? There is no change in density. And we can take this out of the gradient operator. So rho del v is going to be equal to 0. We can take rho to the other side. So we can essentially remove rho from here. And for an incompressible flow, we'll get to this equation, which essentially tells you that the rate of change of volume of a fluid element is 0, which is the definition of incompressible flow. Rate of change of volume is 0, right? And for an incompressible, you can't really change the volume of a control system, essentially. We also have another form of this conservation of mass, which is called the integral form. And the integral form is essentially the integration of your differential form over just the appropriate domain. The volume integral of changes of density with respect to time plus the volume integral of the gradient of rho v dv. And this stands for volume. Whenever you see V like this is talking about volume. I just want to make sure that you don't confuse it with velocity. Right? So this is velocity, but your book uses regular V. This is volume. Look at this equation here, and this is equals to 0. Look at this equation here. And go back to the integral theories we had in the previous lecture. Pretty sure you have your lecture note. We had 3 integral theories, right? See if we can change this from a volume integral to a surface integral. And tell me what it is. So let me rewrite the equation. This part of it is going to remain a volume integral plus it should go the other way around, right? You have it's the second one in your notes. The divergence theorem, right? I'm looking at it right now. And what was your name? Will. I'm looking at it at Will's notes. It is going to be the surface integral of, on the surface, can you just read it to me? A is here rho v, right? That's vector A is rho v. So it's going to be rho v n, right? That's what you have there, right? ds. And this s is referring to the area. Or we can use A. I don't remember if you... So we use the divergence theorem to change this from a volume integral to a surface integral. What is the importance of this, though? When you are dealing with a surface integral, it's a double integral. Integral on the surfaces. So let's go back to this control volume that we were dealing with. This one. When we are taking the integral over the volume, we are taking the integral inside of it, right? But the integral on the surface is the integral over the boundaries, this boundaries, at the top boundary, which essentially eventually can simplify this to m dot in equals to m dot out, right? This is the integral over all of the surfaces of the control volume. How can we get to this m dot? We first have to assume that velocity, rho, and don't really change. That's the first assumption. So this integral becomes rho VA. Simply, but I can take the rho Vn outside, and integral of A becomes rho VA, which is the definition of m dot. Pretty simple. So for uniform velocity and uniform density, not constant density, this will be your conclusion from the conservation of mass equation. Do we understand this equation? Yes. Yeah, one yes, only one yes. The rest of you either are not listening or don't understand it. If you're not, yes.
What is the n?
That's it. That's actually, I wanted someone to ask this question. What is this n? When you are taking the volume integral, you are taking the integral for all velocities in every direction, right? So the velocity vector can be in this direction. Let's go back to this control volume. Can be in this direction, inside of this control volume. When you transform it to the boundaries integral, the surface integral, it has to be the velocity that is normal to the surface, either going in or coming out. It cannot be this velocity, right? But, which is going to make things easier if you were to take this integral actually. So we are taking the dot product of this vector and the unit vector of the surface, n, right? Unit vector of the surface, n. Let's say your real velocity is in this direction. You're essentially finding the projection of this vector on this unit vector. So we are only taking the velocity that is normal to the boundaries. That's what it means. Thank you for the question. What was your name?
Safe.
Safe. I keep asking these names until I can memorize them. Any questions? So we are all clear on the on these two equations. If I ask you a question that needs these equations, you can just take them and solve the problems. Yes? Okay, let's go.
Professor, the reason why we take 3 integrations on that end is because of volume, and then 2 because of the area. What is A?
A is area, yeah.
Yeah, that's why we take 2 integrations. So
Double integral only applies to an area, right? A triple integral applies to a volume, right? It is always the case, yes.
And the volume, the upside down A, that is the control volume? Or is that just?
This is over the whole volume, yes. So this essentially, this V means over the whole volume, this A means over all of the areas, which means that over all of these surfaces, right? And if you were to take the integral over a curve, which we will, we usually use S, integral over S, which means integral over all of this curve. That one is just a linear integral, but it goes over a curve. Okay? Okay. So if you are comfortable with this mass conservation energy equation, let's solve an example problem. This example problem is in your notes, but I didn't print it out because it didn't have that big of a text. So we are given, this is a 2-dimensional case. We are given the component of velocity in the x direction, negative ky divided by x squared plus y squared, and component of velocity in the v direction, kx, x squared plus y squared. And we are told that this flow is incompressible. And we want to make sure, we are asked to make sure that these velocity components satisfy the conservation of mass, which essentially means that these velocity components can be a correct velocity component for a real type of flow. And k is just a constant. It can be any number, 1, 2, 3, 4, whatever, right? So how should we approach this problem? How should we solve this problem? We want to make sure that these velocity components, first of all, this is a 2-dimensional flow. That's the first conclusion you should make, because we are only given 2 components of velocity. Yes?
I was going to say the first thing you want to do. I was going to say the first thing you want to do.
The first thing I want to do, what is it?
Define the control volume.
Define the control volume. It is much easier than that. So you don't really need to go that deep. Yes? Set them equal to each other?
yeah,
Why?
to
So you're saying that U has to be equal to V.
because of the conservation of flow.
Conservation of mass.
Of mass.
Okay, but go back to the equation. Did we have such an equation? Go back to the equations you just wrote in your notes. Let's deal with the differential form. we never said the components of velocity have to be equal to each other. Okay? So what should you do? First of all, this is an incompressible flow. Yes?
It's a U plus V equals 0.
Why? Where do you see that here? We don't really have U plus V equals to 0. Right? What is the equation that we have to work on? Conservation of mass for an incompressible flow. Del dot V equals to 0. Exactly. That's the conservation. That's the equation we want to deal with. It is an incompressible flow, and we are dealing with the conservation of mass. So del V equals to 0. This equation is also called the continuity equation. For an incompressible flow, conservation of mass is also called a continuity equation. So let's expand this to its components. In general, the gradient, let me actually start from the beginning. We have this del operator is partial xi plus partial yj. You don't have to do this every time. I'm just doing it to make sure you understand what is going on. So this is the del operator. This is the expansion of the del operator. And the velocity component is going to be ui plus vj plus wk. Right? The idea is here w is 0 because it's a two-dimensional flow, which take this third term out as well. We are only dealing with these two terms. And if you do the dot product, you will end up with this. Partial u partial x is equals to partial v plus partial v partial y is equals to 0. So for an incompressible flow, the gradient of velocity in each direction has to be equal to the negative of gradient of velocity in the other direction. Does this make sense? Okay. So what are the velocity components? For x, for u, we have negative ky x squared plus y squared. This has to be equal to partial y of kx x squared plus y squared. So we can take the negative signs out, and we only have to take the derivative. What is the derivative? How can we take the derivative of this ratio? Let's say I'm taking the derivative of f divided by g, two different functions. What would this derivative look like? Do we remember from mathematics, calculus?
Is it inverse tangent?
Inverse tangent.
Are f and g
Just two
related to
functions.
x?
Yes, that's f of x, g of x. The same as here. The same as regular.
Yeah, it's differential of f minus differential of g.
Differential of f multiplied by g, right? Minus differential of g multiplied by f divided by
Minus g squared.
g squared. That's it. Exactly. So let's do this. For this first one, what is differential of f? This is ky. This is not a function of x. So differential of f is going to be 0 multiplied by g x squared plus y squared minus different derivative of g, which is going to be 2x multiplied by derivative, or not derivative, f itself, ky divided by x squared plus y squared to the power 2. This has to be equal to derivative of, we have to do the same thing for the y. So derivative of f is again 0, because this is not a function of y, the numerator, multiplied by g x squared plus y squared minus derivative of g, denominator, which is going to be 2y, multiplied by the numerator, kx, divided by x squared plus y squared to the power 2. The zeros, we can just take them out.
Wait a second, the F and the G, was that, you said that was the same as the U and the V?
No. The f and the g are the numerator. This is f, this is g.
I see.
This is f, this is g. Okay? So we can say, we can simplify this. 2x ky is equal to negative 2y kx, which are the same thing. So the right hand side and left hand side are equal to each other. So these velocity components satisfy the continuity equation. Any questions? No? Okay. So next part, hopefully by now we understand the conservation of mass. Next part is the momentum equation. Momentum equation. Okay. In order to understand the momentum equation, actually this applies to conservation of mass as well, we have to understand a couple of mathematical methods and definitions, right? Let's first talk about the Eulerian versus Lagrangian method. Lagrangian. Are we familiar with these two different perspectives? Mathematical perspective. Yes. What are they? What are those? Eulerian and Lagrangian. Yes. Yeah, can you explain a little more?
Euler's method?
What is the Euler's method?
Is that different than Eulerian?
What is the Euler's method? I don't know what the Euler method is. There are millions of Euler methods, right? In different fields. I mean, not millions, but there are a couple of those. Yes?
Doesn't one follow the flow and the other one follows like a static frame of reference?
You are very warm. You're actually correct, essentially. So Eulerian method is by defining a control volume, we are going to look at the movement of flow or force or energy in and out of the control volume or control mass, whatever that is. So you have a frame of reference and you look at the changes inside that frame of reference, right? For the Lagrangian method, you are going to sit on the particle and move with the particle. So you are essentially tracking the movement of each particle. In this course, we are mainly going to use the Eulerian method to do the analysis, right? But it's also possible. I mean, the differential forms of equations are usually Lagrangian methods. We are looking at one small element of the flow and its movements. Okay, so that's just one introduction out of the way. The other thing is a mathematical, method. Material or substantial or total derivative. Or substantial or total derivative. Okay. Are we familiar with this type of derivative? No. I know I covered this in my fluid mechanics course. And we have a couple of students from my fluid mechanics course, which I'm not going to put on the spot because, I didn't remember this coming out of the fluid mechanics course myself. when I was a student. So yeah, let's go back. Let's try to talk about the material derivative. So we usually start by acceleration, talking about acceleration. How do we define acceleration for a solid particle? How do we define acceleration for a solid particle? The derivative of velocity with respect to time, right? Don't make things complicated for yourself. Pretty simple. The derivative of velocity with respect to time, right? Can we apply the same idea to a fluid particle? Sure, but it's a little more complicated when it comes to fluid particles. That's when the material derivative comes into play. So when you're dealing with a fluid particle, the acceleration is the total derivative of velocity with respect to time. But what does this mean? What is a total derivative of this with respect to time? Let's look at this coordinate system, an element, and also an element of the fluid. It's a small element inside the fluid. And we are talking about acceleration. Acceleration over time can refer to the change of velocity of this fluid particle, specifically. This specific fluid particle, right? Over time. That the magnitude of velocity. But this is a fluid particle, so the particles can move away from each other, right? But it can also refer to the spatial change over time. So the change of location. That is also a function of its velocity component, right? Over time. Does this make sense? So change of the value of velocity and also change of the location. Which essentially, think about it this way. If you have a hard time understanding this, think about it this way. Let's say your particle is moving with velocity u, right? After a certain time, your particle will be here, right? If you have another particle with velocity u2, which is smaller than u1, it is going to be here, right? This doesn't happen inside the solid. All of a sudden, moves with the same velocity, right? So all particles are going to be at the same location compared to each other, right? You don't have any expansion or you don't have any movement of the particles. That's why this makes it a little more complicated when it comes to fluid. So we define the acceleration inside a fluid, or acceleration of a fluid element as the changes of velocity with respect to time plus, and this is the fun part, velocity multiplied by the gradient of velocity. So velocity multiplied by the rate of change of volume, right? So the rate of change of volume plays an important role here. That's what we define acceleration. And this is derivative of total derivative. This is called the total derivative or material derivative or substantial derivative, which is a little different than just a regular temporal derivative. So this has a temporal part, meaning a time-dependent part, as well as a spatial part. This is the general definition of acceleration, but when you're talking about a solid, this part is always zero, so we don't really talk about it. You have a question?
I have a question.
Sure.
Did you say one of those V's in there was volume?
No, if you recall, we talked about the gradient of velocity, and we said it signifies the rate of change of volume. Right?
Right.
Not just the velocity. All of the V's here are velocities.
Gotcha. Thank you.
Sure. So in general, we can define this for any parameter. Let's call this d dt. The material derivative is defined as partial t plus v delta. So let's say you are interested in the material derivative of temperature. dt, the changes of temperature with respect to time and location. What does this mean? What does the material derivative of temperature mean? And I usually give this example in my classes, right? If we turn off the AC in this room, what is going to happen? The temperature is going to change. It is winter, so probably we are going to, temperature is going to drop, right? That is going to be the temporal change of temperature. The energy source is turned off. We are going to lose some energy. Temperature is going to drop. But this part is talking about the temperature of your body when you move from this location to the outside, right? The temperature of your body is changing, but not because of the loss of the energy source, because of your movements, right? Because you are moving from this location to the outside. So there is some temperature change with respect to time, but it is because of some movement, some velocity. And how fast you are moving outside is also taken care of here, because there is a velocity component. Does this make sense? Do we understand the material derivative now? Okay, and this I can apply to any parameter. It doesn't have to be velocity or thing. We can have the material derivative of anything. So we also have the general definition. Okay. So using this, let's talk about the conservation of our momentum equation. Let's talk about the momentum equation, the linear momentum equation. And this one we are going to try to understand a little better. I'm not going to throw the equation at you. So momentum equation, linear momentum equation, talks about the rate of change of linear momentum. Do we remember what law governed the change of, or talked about the change of linear momentum? The second Newton's law, exactly. And what did it say? It says that sigma of forces is equals to changes of linear momentum with respect to time. A more common form of the second law is this, right? But that is assuming m is constant. We are not going to assume m is constant. So we are going to use the more general form of it. Second law, Newton's second law. So sigma f is equals to rate of change of linear momentum with respect to time. But this rate of change is not just a temporal change, it's the material derivative of it. Let's make it a little more general. So the other form you have seen in your dynamics course, dmv dt, right? But the material derivative, I assume you haven't seen before. So, and again, we are usually dealing with specific parameters here. So we divide everything by a volume, by the volume. So we are dealing with the rate of change of rho v with respect to t. Okay? And this is essentially the momentum equation. This is the most general form of momentum equation in fluid mechanics. For our application, though, we have to try to find the forces that are applied to our fluid element. Let's say we have a small element, a small fluid element, or a control volume, doesn't really matter. What are the forces? Let me make it a little bigger. What are the forces that is applied to this control volume? We have this element of fluid. What are the forces that are applied here? Yes.
There's like shear force and gravity.
There's shear force and the weight, right? Gravitational force, right, exactly. Shear stress, which is denoted by tau. and the gravitational force. And what is it again?
Let's say you got a normal force on whatever it sits on.
You also talking. No, this element is just floating in the space, but you have the normal pressure as well, right? Normal pressure. So we have three main forces that are applied here. So on this left-hand side, we have to include these three main forces. How can we transform pressure to a force? Pressure is force, yes.
Multiplied by the area.
Multiplied by the area. Since we are talking about the general area, we cannot really simply multiply by the area. We don't really know if it's a rectangle or not, right? So we have to take a double integral of pressure with respect to area. Instead of just simply saying P multiplied by area, we have to write it like this.
Question, Professor.
Yes.
Didn't we specify the volume we're looking into? Can we not tell the area using that?
We want to make it as general as possible, right? So we don't want to, but eventually you are going to simplify this when you want to use it, and you are going to apply it to your special case, but we want to have the most general case possible. So, and let me actually use area. The double integral over the area, P d area. And this is applied only to the boundaries. Okay. What about the shear force? It is going to be the same thing, but our perspective of shear is a little different here. So I'm just gonna write no, it doesn't apply to the volume, no. But it is not as simple as the shear force in solid mechanics. So I'm just going to write down the viscous forces, which is not a bad idea. It is a good way to introduce you guys to the idea that the viscous forces are the result of shear stress. So whenever you neglect viscosity or shear stress in a fluid, you are essentially neglecting viscous forces, okay? Which happens in inviscid flows. And then the only other force that remains here is the body, the volume, the weight. And how do we calculate the weight? It is essentially your density multiplied by the volume, right? But again, since we don't know whether density is changing with respect to volume or not, we are going to take the integral here as well. So the plus the triple integral of, it's a volumetric integral for this one, rho dV. Any questions so far? We have the forces, yes.
Is that viscous force included in the integral, or is it just added?
This itself is the integral of shear, dA, right? So it is not included in the integral. Okay. Yes.
Why does the viscous force not have an integral?
Because, okay, let's talk about it. I didn't want to go into it right away, but let's talk about it. Tau dA, right? That's how it should be defined, and that's how it is defined. How can we calculate the shear stress in a fluid? How do we calculate the shear stress in a fluid? How do you relate the shear stress to Reynolds number? Reynolds number is related to viscosity, right? So it is not related to shear stress. It is not, right? How do we calculate the shear stress inside a fluid? Any ideas? No. In a fluid, shear stress is related to viscosity and the gradient of velocity normal, gradient of this velocity normal to the surface. Okay? So it is not as simple as just a shear stress on a solid, right? And when you plug this in, the differential form, if you assume viscosity is constant, the differential form is going to, the differential, not this form, is going to look like this. The Laplacian of viscosity multiplied by the Laplacian of velocity. Okay? So since it's a little more complicated than just a pressure gradient, we just are going to refer to it as F of viscous. Let me ask you this one question though before moving forward. Is this a correct representation of weight, that body force? And then before moving on, let me just tell you, we have two types of forces here. We have surface force that only apply to the surface of this boundary, surfaces of this boundary, and we have a body force that applies to the whole body. Weight is a body force. Is this a correct representation of this body force, weight? How do you calculate weight? M multiplied by gravity, right? But this only gives you M. Doesn't give you any gravity. So we have to multiply it by a gravitational force, which your book uses the small vector F for, just to make sure that we are talking about any gravitational acceleration in any direction, right? So we are including everything. We are not going to use G here. So forces, the integral for forces on one side. What time is it? Forces on one side. And then on the other side, we have the total derivative of the linear momentum. If we assume density is constant, or doesn't change with time and space, we can rewrite this equation as this. And if you, let me actually give you the intake. I'm sorry. I made a small mistake. I gave you the differential form. So partial t of rho dv dt. This is a volume integral. dv, right? Yes. Plus the surface integral of rho v ds dv. And here we have already included, we have already applied the divergence theorem to transform a volume integral to the surface integral. But this is just an expansion of the material derivative. It's nothing else. We can have the differential forms. Differential form is going to be a little, I guess, easier to comprehend. I'm not going to assume density is constant here. Just going to put it in everywhere. V del rho V equals to negative gradient of pressure plus your viscous forces. I'm just going to write how to calculate the differential form of it, plus rho multiplied by your gravitational acceleration. Okay. So this is the differential form of the momentum equation. And this is the integral form of the momentum equation, this whole thing. It is very simple. It's just a material derivative of linear momentum is equals to the total of the forces that are present here. Just have to make sure you calculate the correct forces, right? And the differential derivative is, the differential form is essentially the same thing, but you're looking at a small particle, the Lagrangian method, right? Any questions? Okay. And since this course, in this course, we are mainly going to focus on force calculations, right? Lift and drag. So we are going to use this momentum equation that relates linear momentum to forces a lot here, right? I mean, we are going to use it in general. Let's see how we can apply this to a case of airflow inside a wind tunnel, right? And let's see if we can find drag. What time is it? Let's say we have this wind tunnel. And it goes from A to B here, I to H here. And we have this airfoil inside this wind tunnel. There's uniform velocity coming in. And after this airfoil, as you would expect, the velocity distribution is going to be different. So we have U2 and U1. Of course, U2 is going to change in the y direction, but U1 is just uniform. Okay. Let's take this integral form and try to apply it, simplify this for a simple wind tunnel. Okay. First of all, the assumption here is that we are dealing with a steady state case. How can we make sure that we are dealing with a steady state case? You just have to make sure you run the wind tunnel for enough time. You run it for like 10 minutes to make sure it is a stable flow, meaning that the flow regime doesn't change with respect to time. So how can we, based on this assumption, how can we simplify this equation?
Just be that dv dt is equal to 0.
This part of it, partial t is 0. The material derivative itself is not 0 because the material derivative has a spatial part, right? Just a temporal part of the material derivative. The changes with respect to time specifically is 0. So this part of it is going to be 0. Second assumption that we usually make here is that the viscous effects and the gravitational force are negligible because we are dealing with air, are negligible. Okay. How is this going to change our equation here? This body force will go to 0. This viscous force is going to go to 0. But let me ask you this. Do we have any forces? Do we have any extra forces here that wasn't present in a general fluid element? We have an object that is immersed in your fluid, right? That airfoil is immersed in the air, right? We can't really understand this because we are all immersed in air, but essentially this is an immersed body, right? What is the force that is present here that wasn't present in a just general fluid flow? Drag force, right? So into this equation for this specific case, we need to add a drag force. Okay. This is a low speed flow. We assume viscosity is negligible. That's usually the case. We will talk about it later as we move forward. But this is given to you, and you are told to assume this is negligible. Okay. And the drag flow is in the other direction compared to the drag force. It is in the other direction compared to your generally, so it has a negative sign. Okay, and what can you say about this integral? You have to design your wind tunnel in a way that its pressure is uniformly distributed. That's by design. That's the design of a wind tunnel, meaning that this integral of pressure here, the pressure difference here and here, has to be the integral of pressure over these areas all over this surface is 0. So this part also cancel out. See? It becomes very easy, very fast. So the only thing that remains is the integral of d prime, and this is integral over the area. Make sure that you are clear on this. This ds can also be rewritten as dA. So we are going to be this equation. The drag force is the double integral of rho v dA multiplied by v. And we are only interested in the forces in this direction. It is actually very important. Momentum equation is an equation about the vector. So momentum equation itself is 3 equations. We can have the momentum equation in each direction, right? Drag force is the force in x direction, right? So we are only interested in that component of momentum equation. So what is going to happen to this? This velocity term is going to turn to u, the component of momentum equation, component of velocity in the x direction. Negative double integral of rho v dA multiplied by u. Okay. So let's take this integral. First of all, this is a 2-dimensional case. For a 2-dimensional case, we are always going to assume a unit depth. Okay? We're always going to assume a unit depth. So this dA becomes, depending on your direction, it becomes either dy multiplied by 1 or dx multiplied by 1. Right? Because we are going to assume a unit depth, 2-dimensional case. Because this is the area we are interested in, the cross-sectional area, right? And the idea is this integral applies to all boundaries of this control volume. So this boundary, this boundary, this boundary, and this boundary. What are the velocities in this boundary and this boundary? It is 0. Right? So the momentum equation there doesn't really give us anything. And we were not really interested in those boundaries as well because we are only interested in the x direction. Okay, so we are only going to take this integral from I to b and from I to a and h to b. Right? Double integral. And since this is dx multiplied by a unit depth, this double integral becomes just a regular line. It is going to be rho, again v, dy multiplied by u. What is the u from I to b, I to a? u1. So this becomes u1. Okay. And then,
Why is it u1 again?
because we are looking at this boundary, the velocity at this boundary is u1. Okay. And we also have h2b, rho v, dy. Here we have u2. One thing that remains here that we haven't discussed yet is the direction or the sign, negative or positive sign. I've used positive sign for both of these, but should it be positive? And the answer to it is pretty simple. If the flow coming out is in the same direction as the normal vector, then you'll have a positive sign. Normal vector of this area, right? If it's in the opposite direction, then you'll get a negative sign. Because if you recall, we had V dot N, right? That was in the divergence theory. That dot N, if they are in the different directions, is going to give you a negative value, right? You remember this? Because the theta between them, this is a dot product. The theta between the two vectors is 180 degrees. Cosine of 180 is negative 1, right? Okay, negative 1, and then we're going to have negative, and we're going to have positive here. What can we do about this velocity, though? This is still the general velocity vector with all three components. And all of these components can be a function of y, right? Go back to the problem. Look at this. The velocity that's given to us is only in one direction. So you can safely assume that we don't really have any movement in the other directions. Y changes as you move, U2 actually changes as you move from H to B, but it is still the velocity in X direction. So your velocity in this direction is going to change as you move a little higher, right? It is still the velocity, so that's the only velocity that is present here. So we are going to take this out and get the U. For I to A, V is U1. For H to B, U is U2. So let's rewrite this. D is negative. Negative integral of I to A. Rho U squared dy plus H to B rho U2 squared dy. So this is the momentum equation for this type of flow that is going to give you the drag force. We can simplify this a little further by using the conservation of mass equation or continuity equation here for this case. Continuity equation tells us whatever comes in goes out. So m dot in is equals to m dot out. Or we can use the divergence of velocity, all of those things. It is going to give you the same result. And essentially the integral of u rho u dy, rho u1 dy from I to A is equals to the integral of rho u2 dy from H to B. Rho u dy is rho ua, your m dot in. So m dot from I to A is equals to m dot from H to B. Is this clear? Okay, we can multiply both sides by a u1 because u1 doesn't change, it's just a value, just a number. We assume the uniform velocity, so this doesn't change. And we can take it inside these integrals. This side is going to be rho u1 squared. This side is going to be rho u1 u2. What is the benefit of this? We are changing this integral that goes from I to A to, yes, H to B. Pardon me?
E2 squared.
No, because we multiplied both sides by a u1. This was the original equation, right? Then we multiplied both sides by a u1. We cannot multiply by one side by one number and the other side by another number. They have to be both the same.
But it's squared above.
This is a different equation. This is the momentum equation. This is the continuity equation. So if I do that, then we're going to get rho u1, u2. We have this integral here and also here. So I'm going to substitute this for this. Your drag is going to be negative H2B rho u1 u2 dy plus h2b rho u2 squared dy. Since the boundaries of these two integrals, the limits of the integral are the same, we can combine them. Let me actually take this inside the integral. Rho u1 u2 negative plus rho u2 squared dy. Then I'm going to bring this negative sign inside as well. We're going to get rho u2 squared minus rho u1 u2 dy. If we assume density is constant, we can take the density out. It's going to be equal to h2b rho u2 multiplied by u2 minus u1 dy. I probably messed up a negative sign somewhere. This has to be u1 minus u2. But you get the idea, hopefully. Okay, so this is a method developed by NASA engineers in the early 20th century, yes.
Why is there still a rho term inside the integral in the...
I'm sorry, that was my mistake. Yeah.
And is that u2 is supposed to be squared as well?
No.
Oh, because you took the...
Yeah, I took the u2 out, yeah. The only thing that is messed up in the derivation is a negative sign, which hopefully you'll figure out if you go over it. And this was the method developed by NASA engineers to have an idea of the drag force inside the wind tunnel. Is this clear? Yes. Are we ready to give a quiz on this? To take a quiz on this? Let's try. No, let's try next on Thursday, right? We can have the same analysis for the lift force here, and if you just do the same thing for the lift, you are gonna end up with this equation: PL dx minus integral of from a to b pu dx. Essentially, the forces that are applied on the lower side of your airfoil minus the forces that are applied on the upper side of the airfoil, of upper side of the wind tunnel. Forces here, which means that if you measure the pressure here, and measure the pressure here, you can have an idea of the lift force that is applied to this. And they use actually these two equations to characterize a lot of airfoils. At that time, it was called NACA, the organization. That's why you see all of these NACA names, NACA 2412. For example, NACA 2412 is a very famous one, right? For all of these airfoils. Okay, so let's stop here. This was a very math-heavy lecture. Hopefully all of you followed what happened. We are going to start with a quiz on Thursday, and then we'll talk about your project a little bit, and we'll move on with the rest of chapter 2.